morning, everyone. I'm Luis Correia with the IST at the University of Lisbon, and I'm also the chair of the steering committee for EuCNC and the 6G Summit, so it's a pleasure to be here. And I would like to thank you also for attending this conference. And as you know, we have two well-known speakers this morning as keynotes. So I will skip reading their CVs, because then I would spend most of the time reading the CVs and not giving the talk, right? So the very first one is Petar Popovski. It's a colleague from Aalborg University. And once again, you can see all the details of his CV in the website and all the platforms. Petar, the floor is yours. Thank you.
Thank you very much, Luis. Thank you for inviting me. Thank you. So I'm going to talk about the role of wireless systems in the interplay of physical and digital time. And I'm coming from Aalborg University in Denmark, but I also have a guest professor position at the University of Bremen. And this research, which I'm going to talk, is supported by the Danish Velux Foundation, but also by the EU project 6G Goals, which we are also going to have presentation later today within the sessions. So this is the outline of my talk. So I'm going to tell some words about 6G. There has been a lot of talk about that, so this is just a little bit addition on what we think that 6G is going to bring. Then I'm going to speak about how latency is modeled, and latency was a big topic of 5G and it continues to be a topic in 6G. But in 6G, latency gets a bit more complicated, and that is what I'm going to talk next. And finally, let's say the second part of the talk is what this interplay between physical and digital time is going to mean for how we perceive events, what is their causality and what is their simultaneity. And it's something that maybe doesn't have an impact now, but if we continue to integrate physical and digital worlds, is going to have a significant impact in the future. So about 6G, one thing that we can conclude is that the ambition of 6G goes beyond connectivity, because we are talking about localization, positioning, sensing, reasoning, and so on. And there are a couple of emerging applications that are increasing the fusion of the physical and the digital world. For example, is the digital twin, is the metaverse, extended reality, or similar. And this is so in some sense, this triangle of 5G, which had the ambition to solve the connectivity problem completely, it's going to be augmented towards including localization, sensing, and everything is going to be glued by intelligence, reasoning, inference, and similar. And then there have been a lot of use cases that have been talked, and there is this IMT 2030, which talks about use cases of 6G. But I just want to mention one non-standard use case which came out of the discussion with people working with rehabilitation engineering and bionic limbs, artificial limbs. They actually have a need for this kind of system. And according to them, this will be the 4th generation of bionic limbs, because there was a mechanical, there was analog, there was digital, and when they realize that they can have it connected, they say, okay, we are going to move to the next generation of limbs. And these are interesting use cases for us from a technical point of view, because there is reasoning, there is intelligence, there is timing constraints, and so on. And there are a couple of interesting there. For example, the exoskeleton. The exoskeleton, which it is expected that it will be used more for elderly people in the coming years. So the exoskeleton needs to have a reliable connection so that a person can remotely intervene if anything unexpected happens with the exoskeleton. So that will probably bring a higher acceptance of this kind of technologies among the population. So as I said, 6G is augmenting the connectivity horizon. And one straightforward augmentation is the use of ISAC, integrated communication and sensing. So in some sense, having the sensors and actuators, we are putting a bridge, microtunnels between the physical and the digital world, because through the sensors, the physical world enters the digital world, and opposite, through the actuation, we are having digital commands that are entering into the physical world. So once we have this, we can say, okay, the data that is collected from the physical world could be used in 3 principal ways. One is to train some algorithms train some machine learning algorithms. Another is to use it as an input to do some inference. And the last one is to store value, basically to collect the data and maybe use it later on for training other algorithm or making other inference or similar. And there's an interesting paper in IEEE Computer from last year, which is called Surprise-Inspired Networking. It's from a networking person who says that basically the main generation of information will happen at the edge. So basically at the wireless access. So we have to, all the algorithms have to learn how to harness this data and operate with this data. So the next thing is how AI and ML are going to affect the communication systems. So the question that we can ask here is how are the communication protocols affected by the growing intelligence in the node? And this came up yesterday in the panel as well about what standardization means in the age of AI and ML. But the point is that instead of having deterministic state machines like the protocols that are now, we are going to have probably modules that are doing reasoning and are not strictly following the prescribed rules. So the question is, how are we have to evolve the protocols in order to conform to this growing intelligence in the nodes? And I'm going to come back to this in a second. Just another thing that is augmenting the networks, which is also obvious augmentation, is augmenting the coverage. So we're also going towards non-terrestrial networks. And this is the non-terrestrial networks are augmenting the spatial-temporal horizon of wireless mobile networks. And also the fact there is that in LEO networks, we have the infrastructure that is moving rather than the user that is moving with respect to the infrastructure. So this is, from a technical point, the integration of these networks that we also heard at this conference is interesting. But I think from a conceptual point is expanding the usual spatial temporal horizon, right? Because we need 2-3 milliseconds for the uplink transmission and if to the LEO and then 2-3 milliseconds to come back. So we cannot speak about 1 millisecond latency only due to propagation, right? And then another recurrent topic within 6G is the issue of semantic communication and goal-oriented communications. So we can say that this came from 6G's search for meaning, so finding other places where we can expand the development of the usual communication systems. So if we go to the linguistics, they already have 5 different domains. There is a phonology, morphology. Phonology corresponds to physical layer. Morphology corresponds to packets that are meaningful units. Syntax corresponds to the control information and basically the state machines of the protocols that needs to behave correctly. And then on top of that, we have pragmatics and semantics. What we usually cite in this community is the introduction written by Weaver for Shannon's paper back in '61, where he talks about 3 types of problem: level A, level B, which is semantic problem, and level C. I'm not sure that whether he was aware of pragmatics, semantics, and the other linguistic categories, but pretty much level B corresponds to semantics and level C corresponds to pragmatics. And why is this interesting for our community? Because it's covering a research vacuum in above the technical communication problem in semantic and goal-oriented communication. And why it is possible now? It is because we are having growing intelligence in the nodes. So suddenly we do not need to follow prescribed, as I said, prescribed messages of state machines, but we can do something on top of it by using intelligence. So the next thing we are about to talk about latency, and then there is a general tendency in 6G to speak about lower latency scales. So for example, in this IMT 2030, we say that the latency is between 0.1 and 1 millisecond. In my opinion, going just to smaller latency, it doesn't say that the system is more advanced. We actually have to look into the timing requirements very carefully and adjust the timing requirements to the operation in question or the system in question. For example, the O-RAN Alliance defines 3 types of timing categories. There is real time, there is near real time, and there is non-real time. And they have different timing constraints, going up to second, dealing with hundreds of milliseconds, and so on. So we cannot just say that in 6G we are going to go to 0.1 millisecond, in my opinion. because there are other types of timing requirements that needs to be satisfied. So I'm going to come back to this issue, but just at a fundamental level, what is a latency reliability characterization of a system? So latency reliability characterization means that we would like that the system achieves something with a certain precision, for example, delivering a packet with a certain probability by some deadline. So if we just plot here the probability that the packet will arrive at the destination by some time, this probability increases as the time increases, because as the time increases, we can do more things. We can add resources, we can do retransmission, we can add codes, and so on. And then we have the blue line, which is inferior to the red line. So the red line achieves a better latency reliability trade-off, right? Obviously, we would like, in the ideal case, that the latency is 0 and we go directly with probability 1 transmission, right? But this is not possible, both due to physics and both due to the statistics of communication. Then, if there is a certain deadline, then the objective is to be above certain probability of reliable reception by this deadline. So basically, all that we are doing for improving the reliability within a given latency is adding some diversity in frequency, in antennas, in code, and in a number of interfaces, let's say multi-connectivity, to move from one to the other curve and then satisfy the latency reliability requirements. However, in 5G, low latency was one of the main features, and there was very often we discussed about the latency of the wireless part, which was usually 1 millisecond or something around that. And this is actually putting a very high pressure on the wireless part, because if you look into the overall chain of how the system operates, there is a computation, there is compression, there is a core network, and there is a latency. So it seems that we put a very stringent constraints only on the radio part with 1 millisecond, but then there is a lot of latency budget to take from the other parts. The reason for this is, I think this is the layered modularized approach, because we would like to say, okay, this is the wireless part. It's going to offer this very low latency. On top of it, we can build our compression, our computation, reasoning, and so on. But it costs a lot, and you're going to see with some actual numbers that to guarantee low latency all the time, and especially we have to be able not to do it when it's not needed, right? Because then we are going to release some resources in the system. If you look, this kind of latency budget that contains how to say multiple components is also visible in the standardization, right? Because this is taken from 3GPP. You can see that there are multiple layers involved in this chain, and then within these multiple layers, we have different contributors to the latency. So if we do it into a very simple conceptual model, we can say that we have computation, compression, and communications. Of course, it's up to discussion whether these are representative of all cases, but this is just conceptual, right? So each of them is putting latency in the system. This is T1 and T2 and T3. When we have, for example, Open RAN, then we are sourcing components from different parts, and then the latency of individual components is not controlled. So this latency is given to us by the performance of the module, of the producer of the module. And then as the integrator of the system, we need to find a way how to achieve the latency guarantees based on this statistical characterization of the individual components. Then in the second part, you see that we can have some coupling between, for example, the compression and computation, which means that, let's say, they're using the same processor, and then we can find a way how to schedule their time so that to optimize the overall latency for these two modules together. Or if we go to a fully single vendor implementation, then the communication, computation, and compression can be totally optimized for latency. And then even at this, let's say, mathematical level of this, you can see that it's hard to beat the case where everything is optimized together, because then T1 plus T2 plus T3 would be optimized as a whole rather than separate components. So what is the consequence of this? If we take just the expected value, then actually if we have T1 plus T2 plus T3, then the expected value is, of course, sum of those, because this is a linear operation. But what we're interested in this system is not expected value. We're interested in tail events. We're interested in low probability events. And then finding the low probability event of a composite latency is non-trivial combination of these CDFs. And this is what we have done in a recent work, again, with the people from rehabilitation engineering, where we tried to control a robot arm through the mobile edge. And you can see what are the components of the latency. It includes compression, it includes encoding of the feedback of the robot, and so on. So instead of speaking of 1 millisecond, we speak about this whole sequence of latency components, try to model them, and see what we can achieve within a certain deadline. So the main message of this part is that instead of speaking maybe of offering a very low latency, 0.1 to 1 millisecond, we can, in different applications, get some part of the latency budget from the other components and then combine it with the communication latencies. For example, if you take compression and communication, if you compress the data, then the amount of data you are sending is small. That means that you need lower rate, but not necessarily, because the time you spend on the compression decreases the time that you have for transmission, right? So there is a trade-off there, how much you want to compress and how low data rate you want to transmit. Then, beyond latency, we get some complication into the notion of timing, because latency appears to be just one type of timing. Another popular measure that appeared within the last 10 years is the age of information. And age of information and its byproducts turned out to be better metrics for some systems that use sense, actuate, compute cycles. And mathematically is interesting, because in latency, the packet arrives, and then we try to measure what is the latency from the arrival of the packet until the packet is delivered. In age of information, we can actually generate the packet at a suitable time so that the information that is received and processed is as fresh as possible. The thinking here is that the fresher information is more relevant about the state of the world. So the fresher the information about the control system, the better I can control that system, the better I can describe that system. And then there are other measures. There is age of X, age of different things, age of incorrect information, or similar. But for example, one specific thing which we have done, and also experimental, it's experimental work with our colleagues from Bosch, is something that we call age of loop for goal-oriented communication. So the idea here is that there is a AGV, let's say a moving robot, and this robot is sensing, but is not clever enough to decide the control. And then it needs to send the sensing information to a central controller. The central controller processes it, creates a command, and sends it back. And we say, okay, what we are interested in is the time of the loop from the moment when you sense until the moment when you receive back the command. So this is like a round-trip time, but not exactly, because we can decide the sensing moment when we believe that is the most useful for our control problem. So that's why it's age of loop, because we're deciding when to create this sensing information. And then we try to optimize for the time of the loop, age of the loop, rather than for individual latency. And here is the result. So if you optimize using some reinforcement learning, then the resources that you use with this scheme are this RL scheme, which is here. So you use very few resources in order to attain your stability constraint and to control the system successfully. On the other hand, if you give 1 millisecond latency, one for downlink and one for uplink, then the amount of resources that you're using is a lot. So the message from here is that instead of focusing towards 6G, instead of focusing on just offering latency on a link, we might might try to optimize the control loops. Then we can have a more general timing constraint. For example, usually we think about Shannon's model as a push-based communication. So you think about Shannon's communication model, and there is a sender that assumes that the receiver is always ready and interested to receive. And this, in the computer science literature, this is called a database with permanent subscription. But we can have another thing. We can have the receiver, for example, let's say we have a digital twin, and then the digital twin, there is an edge server there, and it's creating the model of the environment. And then the digital twin says, oh, okay, for this part, I'm not so certain, so I'm going to pull out information about that part and then update my model. So in that case, the latency it's not the latency of the packet generated at the node, but is the freshness of the information delivered to the digital twin or to the edge whenever they ask for it. So this is what we call, let's say, pool-based communication. And then you can redefine the age of information. Instead of having age of information, you can have query age of information. So we would like to measure what is the quality, the freshness of the information at the time when the query arrives. And there is a conceptual difference between the two types of problem, optimizing the freshness and optimizing the freshness when the query arrives. So I will not talk much about that, but in general, the semantic communication is spot on with this type of pool-based communication, because in semantic communication, the base station or the edge can do some inference and can ask specific questions to the nodes and only get responses that are relevant. For example, it can say, have you seen this type of car? Have you seen this type of animal? And so on. So basically, we are creating a semantic query and sourcing the data within a certain time limit. So the definition of latency within this is different from the definition of latency for a link where we have packet at point A and coming at point B. Finally, latency is also changed by generative AI. And this is an interesting development because in the traditional communication systems, let's take what is an internet? The internet is a multi-hop replicator, right? So we have a source, we have a destination, we generate data at the source, and we make a trustworthy copy of the source data to the destination. But the point is that we can have nodes in the network that are powerful generative AI nodes. So if the latency of the packets coming to these nodes, like to this node here, if this latency starts to be large, then the generative node in the network might start to generate packets towards destination that are acceptable. This is the notion of acceptable perception. Of course, this is against the layering principle, where the intermediate network nodes should not look at the content, but they should just forward and replicate the data. What I'm trying to say is that having the generative AI, having the opportunity for that, and having the possibility to have acceptable content might change the way we're designing this network layer and change our view on latency, right? Because for example, our colleagues from Dresden, they have something that they call negative latency, which is a good term, which says that if you have a good prediction, then things will be, the packet will arrive even before it's generated, right? So the only way in which you can send information faster than the speed of light is to predict it, right? So, and in general, what can be predicted doesn't need to be communicated. And this is a principle that we could use maybe in the upcoming design of the network with a more powerful AI nodes. So finally, I'm coming to the second part for the rest of my talk, where I'm going to talk about these consequences of mixing physical and digital time and how this affects causality and simultaneity. So let's take a simple example of a time in a fused physical and digital world. So we have a base station and a robot, and then we have an event that happens. That this event can be visual and both acoustic, like a thunder here. And this event is sending acoustic waves around. And these acoustic waves are possibly creating another event, E2. But the acoustic waves are picked by the robot, and they're also picked by a sensor, which is nearby. Then you see that these are the physical events, E1 and E2, the events. And now we are looking into how they're entering the digital world. This is the intertwining. So the base station has a sensor, radio sensing, like joint communication and sensing. And using this sensing, it perceives the event E2. Then there is another user that is observing this. And this user might also report, let's say from visual observation, might also report some data. So basically, the blue lines here are digital transmission of data. So the sensor that picked up the data is sending it digitally to the base station, and the user that picked up the data is sending it digitally to the robot. The question here is, how are the robot and the base station perceiving the reality? So for event 1 arrives as a digital event to the base station and as a sensing event to the robot. But event 2 arrives oppositely as a digital event to arrives as a digital event to the robot and to the base station as a sensing event. So you see that the order of the events for the robot, the chronology of the events for the robot and for the base station is not the same. So this is changed. So digital and physical time get intertwined, and the chronology, this is the interesting consequence, the chronology depends on the observer or the data processing. So if the observer is faster, then the data would arrive earlier. So then that event will be even earlier than the other one, right? So it seems that the chronology of the event depends on some physical parameters like propagation and so on, but it also depends on the data processing. So if we look into the physical time, of course everybody knows who this is. And the main point of the theory of relativity was that the physical time is defined by the observers. So the chronology of the event is defined by the observers, but what is absolute is the causality of the event. Because if something is separated, more like in this light cone diagrams, if something is separated with a larger distance, then these events could have not caused each other within a given time, right? That's the cone of causality. So that's one, let's say, of the many complex messages of the relativity, that is the one we are picking up for this talk. But this person probably not many people know, but we probably use his product every day because this is Leslie Lamport who created latex. And besides creating latex, he did many other things. And he wrote this extremely good paper in '78 about how digital time should be counted in computer systems. So when you have concurrent distributed systems where digital events are taking place, so how should they be ordered in order to know, for example, who booked first the flight, who sent first the response to some social network and so on. So these principles were defined back in '78. But what we are talking about today is that we have to put the information processing. And the interesting thing is that the information processing is changing the way the events are perceived. For example, if you know this famous thought experiment of Einstein about who sees the events as becoming before the other, or who perceives simultaneous events, that only depends on the propagation time of light, right? But for us as humans and for machines, the perception of the events depends on the time for processing. So in the second example, we have a sensor base station and a thunder. And then the point is that if the data rate of processing from the sensor is very low, then this time that the base station needs to receive the sensory data is much larger than the time to detect the thunder, right? So if we have in the future, if we have digital twin system where these different events take place, so there could be a total mess into what was the chronology of them. And we cannot have a single history that is consistent. So how to make sense of this? We have to look into how human perception is done. So in human perception, we have multiple types of sensors. We have visual sensors where processing is very slow, but the arrival of light is very fast. Then we have auditory perception where the processing is very fast, but the propagation of acoustic waves is slower. But the brain seems to play out everything synchronously for us, right? So if I knock here, I feel simultaneously a tactile input, auditory input, and visual input. But this is only happening within a given horizon. So if we have a thunder that is far away from us, we all know that we are not going to observe it simultaneously. The reason for this is that this thunder, most likely, is that this thunder that is far away was not evolutionarily important for us. And that's why our system doesn't perceive it simultaneously. But it's also a message for us that if we have systems with different range, satellite, mobile, local network, and so on, the real time and the simultaneity cannot mean the same thing for all of them. So we cannot speak about that the latency should be the same for all these types of networks. So why is this becoming important? Because there are more and more works on perceptive mobile networks. So the networks that are that are taking the physical world into the digital, for example, creating digital twin, creating extended reality, and so on. And this is one of the papers that was advocating this concept. So you can see this at many levels, how you do it at physical level, how you do it with signals, and so on. What my focus has been is what is the consequence of how we measure time. So it's not only about the precision of time. So we can actually use a very high precision protocol like PTP and then have the time ordered there. But that's not the problem. The problem is that the sensing events that we are not that we are getting into the digital world, they are not time-stamped. The nature is not time-stamping the events. So we have to make sense of them based on the order in which they are arriving and based on our intelligence. This is how humans make sense of reality. So this is done by something that is called temporal window of integration. So if you go to the multisensory perception literature, they are discussing this multisensory temporal window, where basically what we say is that we define a temporal window, which for humans could be 150 milliseconds, and the older we become, the larger becomes the window. And then everything that comes within this 150 milliseconds is now. So then is the next now, then is the next now, and so on. So we are observing the world in some discrete chunks. So we do not have an infinite resolution. And the point is that once we perceive the world like this, then we can, this is also decreasing the probability of having causality violation, right? Because if two events come after each other in one place and another way in another place, we say, well, if there is a temporal window, they all come simultaneously within this window. And in this way, we are tackling this glitches in the causality and simultaneity, right? So I tried to model this for artificial, let's say, 6G system, where I took a very simple, generic model of a synchronous sensor. You could think of, for example, radar that is periodically getting the data with some beams. Then also the communication data, and communication data is described by the data rate by which data is processed, for example, for acquisition, compression, transmission. And this is the integrated process where digital and sensing events are coming. And then what we could do is we could define a temporal windows of integration, where we say within each temporal window of integration, everything that arrives is simultaneous. So what is a causality violation? So here's an example of causality violation where physical events is causing a digital event. So we have a physical process, we have some physical event, and then there's a device A, and there's a device B. Device A is perceiving the physical event, and the device B is also perceiving the physical event. But device A, this is the time tau A. Within the time tau A, the device A is seeing the event and then generating a digital event. So you see that the physical event caused some perception at A and B. The point is that the B is perceiving it with this synchronous sensor that has a certain integration time, like every radar has. And then you need a minimal integration time in order to say that the event has arrived. So the event for the device B has arrived after the finishing of the next integration window. But for A, maybe it detected it in a different way, faster, generated data, and sent the data. So this digital event is coming before the sensing event. So we have, in principle, we have a causality violation here, because to an observer, it will seem to the observer at the device B, it seems that the digital event came before the sensing event and might have caused the sensing event, right? And how do we avoid that? We put temporal windows of integration. But these temporal windows of integration do not eliminate the causality violation, because in this specific case, I choose the example where the digital event and the sensing event will come in two consecutive windows of integration. So it's again a causality violation. But they can mitigate this causality violation. This is how humans perceive. And we can say, okay, to make a sense of this example, you can say that from this event, there is an acoustic propagation towards A, and then there is a radio propagation towards B. And you can put the numbers for a base station for, I don't know, 1 kilometer range and so on, and you can see that indeed this can happen. we have a more detailed analysis in the paper. So the question is how to choose the window size W. Well, to choose the window size W, we have to see, we can do some relatively simple analysis, and we can say, okay, the minimal window depends on the processing time of the sensing event, the maximal sensory propagation time, the minimum transmission time of a digital system, and the minimum time that is required to cause a digital action compared to the digital action at A compared to the physical action. So, but the point here is that if the device A is using prediction and generative AI, then this time tau A mean becomes negative. If that time becomes negative, that means that we need to have a much larger window of integration in order to avoid causality violation because of generative AI events, right? And this might be malicious events and so on. But so what is the problem with having a large temporal window of integration? The problem is that larger temporal window of integration decreases the probability of causality violation, but also decreases the throughput of the events. So every event will happen simultaneously. So we need to run certain inference algorithm afterwards to figure out what happens after another. And then you can say, okay, this choice of windows, where have we seen something similar before for a given environment? Well, we have seen it in OFDM, right? Because in OFDM, we are choosing the guard interval based on our best guess about where this system is going to be used. So the guard interval is chosen based on the time of propagation. So what I'm saying here is at the higher level, you can choose a temporal window that takes into account the types of events that you are processing, the range in which you are processing, and what needs to be simultaneous, and where do you want to avoid this causality violation. So you could have the opposite effect. You could have that the digital event causes a physical, and there could be, again, problem of violation. Or there could be also simultaneity violation, where many events are caused to occur simultaneously in nature, based by some, I don't know, some physical event. But the devices that are reporting it, that are not reporting it simultaneously, they're spread over time. So again, you can try to see whether this temporal window of integration could help you to capture the simultaneity of the events. So why is this important for future base stations? So I think that the future base stations will be guardians of this intertwined physical and digital time. Because what we are talking about, 6G, is that they are going to be interfaces between the physical and the digital world. So our community has the responsibility to deliver a trustworthy chronology of the events and deliver it to the applications that are going to process it afterwards. And this is important in at least two ways. One is, using this temporal window of integration, we can set different latency requirements for our communication systems, and that is in a co-design with the applications. And second, temporal forensics, that we have to have a trustworthy account of what was the sequence of events, because in 20 years, we might have flying cars, autonomous vehicles that are causing traffic accidents. So who is going to witness what exactly happened? It will be probably the base stations and the mobile infrastructure. And technically, what are the problems that we can solve? Is we can set the latency and timing requirements for a service. So we can actually define goal-oriented communications where we define a resource allocation problem based on these types of temporal window of integration. And also, we have to learn how to timestamp the events to give it for further processing in the network, right? Some AI algorithms are going to process these events. So we have to do the proper timestamping that is sufficient for that type of algorithm. We do not need infinite precision, because the higher the precision of the events, the higher the power consumption. And if we want to define purely technical problems, then we can go to multi-user systems, see these combined sensing and communication, and define, for example, medium access problems that are allocating the resources that are meeting these requirements. So, but this is not the full story, because if you go to read the literature on multisensory perception, we are not just taking the events as they come within the temporal window of integration. There are three other mechanisms by which humans compensate. One is that the brain uses deeply rooted knowledge to compensate for external factors. For example, when a thunder hits in a far distance, we know that it occurred simultaneously, the acoustic and the light signal, because we have prior knowledge on this phenomenon. then also the brain might be flexible and change the temporal window to adapt to the situation. And here, under each of these, I have put what could be the consequence for the design of a mobile network. For example, in the first case is the causal inference at the edge and the cloud. In the second case is that we can have applications with varying levels of criticality. And also, the brain is actively shifting the time to compensate for gaps. So if something doesn't correspond to the reality that the brain has predicted, then it fills out information in order to make things consistent for the brain, regardless of whether that was correct, exactly like that in reality. And this is what generative AI could compensate within this network. So if the data doesn't arrive, then the edge nodes and the cloud can generate data that is most consistent with what we are observing. So where have we seen this before? We have actually seen it with magicians, right? Because they're using the fact that we are not perceiving reality as it is, but we perceive the reality as our brains tricks us to do it. So this is how they are making their tricks. So the question we can ask is, how will the magicians of the digital era look in 20 years? How will the companies building applications use these effects of intertwining of digital and physical time to make hopefully something good for us, but unfortunately, they could also use it to manipulate it. So this brings me to the conclusion, is that we see that 6G is on a route beyond communication and is looking for meaning. And then we have seen how the intelligence and the other factors like sensing and communication are changing, are augmenting the scope of a communication system. I also tried to outline that timing performance is not only latency of the wireless link, but it also has multiple components. For example, the interplay between communication and compression. And the packet transmission latency is just one type of timing measure, and there are many systems, like, let's say, goal-oriented communications that would use a different timing measure, like the time of the loop or similar. And in the last part, I talk about the intertwining of physical and digital time. And the important the takeaway from here is that the flow of time depends on information processing. Depends how we are processing the information. If we put a very high rate network, very high rate computation, and so on, then the time will pass more closer to basically what is happening in the reality. But if not, then we have to compensate in different ways within our digital twins and extended reality and so on. And maybe now it looks far-fetched, but when these things become integrated, we are going to have to think about temporal forensics, the right order of the events, and the chronology. And this is some very tiny initial effort to outline the problems in this area. So thank you.
Thank you, Petar, for a very interesting talk. And thank you guys for the questions. You have already put the questions, right? No? Okay, no reversing in time. Okay, we have time for a couple of questions. I cannot see the stage, but there are mics around. Anyone with a question? Okay, a microphone on the third row or fourth, whatever it is.
Yes, sorry. Yeah, thank you. So loud. Yeah, hi, thank you for the wonderful presentation. I know that if there's nobody else question, I will always have one.
That's great.
Yeah, my name is Mitch Tseng. I'm with EuCNC from Taiwan, right? So when I was listening to your presentation over there, the things kept coming to my mind is that, so in the future, I don't trust what I see. I trust Nokia base stations. Is that what we are leading into?
I'm not. If your base station is Nokia, yes, but you have to trust the wireless infrastructure. Mm-hmm. And I think again, our community is building the infrastructure. Other communities building the AI algorithms. They are more popular than us now for the moment. Yes. We have to accept it. But at some point, when these algorithms are deployed, then we have to ensure that the infrastructure is delivering trustworthy data to make trustworthy conclusions. And that would be, I guess, our responsibility.
Yeah, I enjoy the forensic part. That's very good. Thank you. Yeah.
Thank you. One last question? No? I don't see any other questions. Okay, anyway, Petar will be here during the coffee break and the whole conference as well. Petar, thank you very much.
Thank you.
I advise not to drink the beer now. Probably it's too early in the morning, but still, I think you can
I'll try to
enjoy
resist.
it in the afternoon.
I'll try to resist.
Thank you very much.
Thanks a lot.
Thank you.
Thank you.
And I think there's
He's coming.
Thank you again. Okay, and then, yes, it's already there. So now we have the second speaker, the second keynote speaker of this morning, and I think it's also well known to the community. It's Wen Tong, he's the CTO wireless of Huawei. So Wen, please, the stage is yours. Thank you for coming.
Thank you, Luis. Thank you, Luis. My talk will be on AI, and to be more specific, will be on the system of AI or for AI. That is, we are not talking about use AI as a tool to optimize our current system, rather than to design a system for AI. I think this will be one of the key, or if it is not the key for the 6G design. So the component I'm going to talk is a run, a core, and a UE. So the past 18 months, basically, it is a revolution for AI, and this revolution that we may not seen for past 20 years. Maybe the previous one is the iPhone, or it's the internet can be comparable. For the past 18 months, what had happened is that the so-called scaling law for AI prevailed. GPT-2, GPT-3, GPT-3.5, that show up with a ChatGPT, and then GPT-4, GPT-4.5, or the couple of days ago, there is a GPT-4.0. Then there are multimodality is the Sora that is start to be available. So what is the claiming will be in 2 years or 3 years, there will be a so-called artificial general intelligence. And then there is obviously a plan announced in 2028 with 1 million GPU cars to build about 500 trillion coefficient model as a biggest cost, the Stargate. And that model need a nuclear power plant to power. The scaling law is still prevail. That means the intelligence, the model, the bigger model, the more intelligence, and in some aspect is already super intelligence. Roughly speaking, in the GPT-4, 4.5, the IQ is about 100, and then GPT-5 later will be 140, 45. So Einstein is 145. So that means we'll have many, many Einstein, like a brain in the machine. The other thing is there are still some unknown algorithms need to develop in order to make it secure and trustworthy and all the other even explainable. However, the model complexity has a big implication not only for the computing community, but for us as wireless or networking people. Because the human level of intelligence, the computing is demanding is very, very big. And Moore's law won't help that. In that case, in 10 years, we do not likely to will have a pocket brain. That means the chip is so powerful that is at the brain level, intelligence will be in the pocket. So therefore, to deliver the intelligence of a human level or even superhuman level need network to do this for this intelligence service at any place and at any time. So I try to point out our human brain complexity is about 100 trillion coefficients in that way. Where now is about 1 trillion level. Give you a rough level, like a dog is about 5.5 trillion. The mouse level is about 200 billion of coefficients. So in the device, the latest announcement is about 10 billion coefficients. So it's a very, very rudimentary intelligence. They can have a probability to compute. But even in 2030, because the device is purely Moore's law dependent, so that's what I said is it is in the 6G service time, let's say, that is still a question. However, the computing in the data center is in the 10-year, 1,000 times speed, much faster than Moore's law to grow. So that will eventually capture the human level of a service in the 2030 or 2028. The scaling law has big implication in why the people are pursue this. So one dimension we can see is the model size and also the training of the model need computing, so horizontal wise. So the more of the computing, you will see the loss is getting smaller. And on the right-hand side chart is the model size with the loss. Again, the loss going down when you have more computing through into the training cycle. And with that, you will have many other, more training, you will have a more so-called emergent. That is the intelligence, or it doesn't even contain in the training side, but they have a more intelligence in a sense. The other very big factor related to the network or to device is the world model. So far, all the digital, the ChatGPT-like big model is in the digital world. They are not yet to interact anything with the physical world or to operate, control the digital world or to take some sensing data from the digital world yet. These are all language model with the language training data set available in the internet. So what 6G will come into a big role is the sensing, or we call the integrated sensing and communication. So this will be, again, a new factor, in my view, will revolutionary to the AI. So there will be the world model is critical. You will see the Lacan has the decision and the feedback and all this in the world model part in order to enable the so-called embodied AI. And these components are right now almost there for the 6G concept we have. So in a sense, we were dealing, if we deliver the AI service, it is a neural network to communicate the other neural network. That will be the most critical and component or the differentiation from the previous generation of the networking we see. And in the case that for my view, we may not need to use, or it's not beneficial to use the AI computing to compute the classical connectivity part, meaning the Shannon paradigm. But rather than we need to augment this to the other level, not at a bit information level, because what really needed is the so-called effectiveness communication with the the effectiveness of the intelligence that it takes the effect. So again, this is an old topic which has no progress since many years, 1949. So the discussion was a level A, that is the technical, how accurate the symbol communication will be transmitted and recovered. So this was solved. The second one is the semantic, how precisely the transmit symbol convey the desired meaning. And this is not many progress or research on this. The third one is more important in this case, is how effectively does the received meaning affect the conduct of the desired way. So this is the one that truly, the AI model will start to come into the play. In this, today's large language model, this means the intelligence is not necessary to represent and stored at the semantic level. They are more sophisticated than the semantic level. The semantic representation of the language model is the token. So we really now come into the token in the transformer or the GPT model. That is not as a real semantic in the language as a syntax level. The token can bridge the human and the machine communication without translation. So this is the foundation. The token will be considered as the basic connectivity unit, may not even at the bit level. Then token provide the common fusion of multimodality, all the sensor, radio signal, image, text, and voice, and all this. And then the transformer in this content is the encoder and decoder for the effectiveness communication. So in the top model, what is actually the bottleneck or barrier for us today is that any application we need a software programming. And then to implement application. This is a lot of industry effort to do that. With this model, it is basically, it's a natural language 2x to anything, that we skip the software development step because the model understands the intent. So that's where, with the transformer as a encoder and the receiver and the token as the really element for the communication, that's where we were coming to. So what is a transformer? Transformer is an auto-progressive computing that generate with a text in or text out, or in the other way, it's a sequence in, sequence out. So it starts to iterate in the output. Today, it is actually the output can be infinity length. That is technically feasible now. In the transformer, there is a small model and a big model, so you encode some prompt and then in the so-called token, and then generate the other output. So that's a generative part. This model is very friendly to the communication model as well. So as all we communication people now, if we view the transformer, it will be as a generator. So like a small text to generate a big text, that's where you play ChatGPT for. And then as a compressor, so you put maybe 10 papers and it will give you a summary, a very abstract with some 10 lines. So this is possible now. As a translator, so any language to any language, and natural language to software, and natural language to software or even executable code. So that is also feasible. These are very impactful consequence in terms of next generation. And transformer as a solver. So these are the happening now, not completely in the ideal mode now. So you gave a intent or requirement. So they will give you step 1, step 2, step 3, and basically reasoning and planning for you to do the things. This will be highly desirable with this 4 if we construct the service. As I mentioned, this token as a universal element now in this entire model that will mix all the modality and generate all the other modality or even software. So the token communication here, we mean it is a very efficient communication sometimes, because if we only care the effectiveness and the intent, we may have 1,000 times of compression. It is reliable because the token is dependent, generated by the autoregressive computing. Even portion of the token are missed or damaged, this can be still reliably convey the meaning. And token is as well as a secure data, because it's not easy to read unless you have the original training data set from model to re-inverse to compute your training data set is computationally impossible. And then, of course, the neural network is a memory. It is basically a Kolmogorov compressor with about 20 times of the language that have been done already. And also the ID. So meaning everybody has its own on top of a fine-tuned model that's belong to you, and that's represent you only. So those are the token model, token communication. So then the architecture becomes this. So we will have a model in the device, in the edge, and in the center. I showed at the beginning some computing feasibility because of the Moore's law, and also the 1,000 law likely will have neuron at the device 10 billion. At the age is 100 billion, so less smarter than the dog, but we have for sure have a human level of intelligence in the data center. Then for the machine to machine, this is the one that we easily implement this. You will have a demonstration in the shop. In the stand over there, and then this was last year. So with an encoder of the transmitter at the transformer at the device side, some 800 meg of size of a model. Then you have a transformer, visual to text transformer, and then use the transformer to talk to the cloud transformer, that a bigger one. So on the cloud side, it's a natural language. So basically, you can start to do a lot of things that it's only, you don't need to program, but you just use the human natural language to control. So these are the typical machine-to-machine communication. And in this case, if it is machine-to-machine communication, not involve the natural language processing, we can have a nicely edge computing to close the loop with the token in between over the air. So that's the token communication for machine-to-machine. If there is on the right-hand side a human being interface with this process, then you need some large language model to translate the natural language into a machine language or the token, so that you can interact in the base station or with the device directly. So far, this one is physically, it's a trial and physically viable, very close to a commercial implementation. So those are the machine communication side. But human being is difficult because we have so-called system 2 that is capture because we have an emotion, we have some irrational things and some uncertainty things need to capture in the system 2. In the model, I talked this several times now. So your model is system 1, that is your deterministic behavior, or it's you. That basically can store in the cyberspace that you can basically talk to any other people with thousands conversation simultaneously because you are dealing with a digital twin, not the real people. So the teleporting of the system 1, I think that's a reality today already if you have enough time to train a large model, let's say 1 trillion or the other, meaning everybody can be affordable to have your own model with that complexity. So in that way, if the computing is embedded in the device, edge and the center, this will be the RAN looks like. Then we don't need to talk about this as a radio. So it's a different entity. For the better of a name, it is a RAN that I will talk in the following. It is not a radio anymore. It is a total integration of sensing, AI, computing, and communication. I'll give you one example. So the so-called integrated sensing and communication for the world model that in the 6G definition is capable to do now is that if we have, for example, a device to do the point cloud sourcing, and we communicate this point cloud from the device of the sensing and to the edge, and then use to build the physical world model. So at the edge, we can use a neural network or compute to AI to synthesize so-called physical world through the transformer. And you don't need a digital twin be a priori be prepared or available. Basically, the radio, where is a radio, where is a signal, where is a 6G signal, where is a digital world, will be automatically generated. We need this digital world to do a couple of things. One is the enhanced communication, because we precisely know the environment of the communication. So in the bottom, that the sensing start to create a point cloud, and point cloud to rebuild the digital world and use digital world to precisely regenerate or generative of the channel model, and then you know how to precise to do communication. And on the top one is the people most of people are talking with, start with a digital twin. That digital twin is typically, and in the practical is still difficult to get everywhere. You have that twin available to you, and who is a supplier of the twin that is another question. With this digital world, now we can use the AI to come into this world to do all the service, because any AI model, when they apply the digital world, they need to do so-called alignment. Alignment to the reality in real time is the key or the necessity for AI model to operate in the digital world. From this angle, so that 6G design should capture this opportunity to make sure it's enable all the other features: massive connectivity, immersive, hyper reliable sensing, of course ubiquitous to be enable this AI service, and to enable the AGI as any node, the base station, the core, the device. So those are the probably that we need to make sure we don't miss the opportunity of this round with the AI. And then the framework is like this. So we are dealing with the token communications. To processing the token, there is embedding and visual to text to video, visual transformers, and the machine to natural language, natural language to machine translator. So these are the transformer has this property. In that case, there are some attention, self-attention, cross-attention, auto-regression, and then those are the key to how to integrate this. And number 3, we're directly dealing with the effectiveness communication to skip all the software translation and development process. Then the number 4 is that we need some model with a foundation model. That's all. So far there are plenty open source available, but then how to fine tune to the individual service and or individual person, that's another fine tuning is critical. Then there will be a generative pre-trained transformer. In this case, most of the time we need a human in the loop in order to have control the risk and the other aspect to align the human value as well. So this part for the networking is more important because we cannot trust any individual, any organization to have a risk-free of the model. So as long as most of people are connected, so there's a community, human in the loop, that's the way eventually to resolve this problem. That's what I think is the unique value to offer from 6G or 5G network. Then the real world time model, as I mentioned, the sensing generate the digital twin, and digital twin represent the real-time world model. Those are the little bit work on the standards part to standards the model and data and some sensing capability, or we need effort to do. The next portion, I'm going to talk about some engineering aspect of this A-run. So first of all, we need to treat A-run as an agent. That means it actually not only a bare model, it carries the tool and the planning, the memory, and some action for this as a computing as a whole, natively integrated with the RAN network. Why need a memory? Because when you do ChatGPT, you ask the question yesterday, and they don't remember you. And they will, you come back today, ask the question, probably they will give you same level of understanding. But if you have a memory as long-term and short-term, as a communication, let's say, interaction more, and they will actually know more efficient in terms of give you answer or help you to do the things. So in that sense, the 3 components is make of the so-called radio access network now is the connectivity, sensing, and AI. So if we integrate connectivity as AI, first of all, connectivity to enable AI is not only the token communication, but as well as some action to the physical world, that is from digital world to the physical world. So we have the URLC from communication to AI to help communication. As I mentioned, there will be the use AI to improve as a tool to improve our communication blocks and other channels. They can be as large as, when these are in the precise physical world, there are some 2 to 5 times enhancement, very large, rather than we assume some simulation model, as we did now in the practice of the design. And then when the sensing and the communication integrate together, so communication to enable sensing, we are up to 5% of overhead for sensing. That should be ideal, fulfill all the sensing requirement. And then there will be a sensing assisted communication, especially the location, beam, and all this. There are very large gain in terms of these communication overhead. To one-shot communication is feasible when you have a sensing. And then the sensing and the AI, of course, sensing will be the alignment to the world model reality, and the AI will help to generate more accurate world model. Use AI model to reconstruct the world model. Last but not the most contribution is the big data is not from the internet text anymore. It will from billions of devices with the sensing capability. That will be the next stage for AI, because right now most of the big model training run out of the data of in the public domain. A few words that the network for AI, which is use the generative distributed learning. That means you don't send the data to anybody to train. You send your local trained data, not federated way, because you need to elect a center to federate. But in that way, if you can send the generated model, you can publish the model for anybody that will indirectly use your data. And or distributed inferencing, so you can do some coded inferencing joined together with one computing to help inference many things, and then use the coding concept or majority vote. AI for network, there are many. Predict the cell propagation and traffic. A lot of academia work already being in this area. And the other one is the reinforced learning to decide best scheduling strategy. This, as a GPT model, more mature to do this, I think it will be a more significant impact. And then there will be a transformer for machine communication. I already showed you the design. And then transformer for system 2 and system 1 for human to human or XR communication. In terms of optimization, this is a more opportunity open now because the deep learning, in principle, they can reach the human level because you are efficient in the learning part. The reinforced learning has a potential to surpass the human intelligence because it can self-oriented set up the goal. Though the goal can be set up that the human, even not outside the human capability, but reinforced learning can be done. That, for example, the chess and the goal that already machine be better than human being. And reinforced learning is a progressive, continuous, less dependent on the large set of data. It's good for example, the network and the product optimization. So I want to point out is if we have the gold play computing power, so we can truly get really optimize the RAM. That's the level of complexity of 10 to the power 300. However, we still have a big constraint that this luxury computing is not available or capable everywhere. We Technology-wise, we progress very well on the spectrum efficiency, and in terms of bandwidth available for the network is also doing very well. And in that case, per bit of the the energy efficient, if we ceiling the per site, the base station has a 700 watts level per the radio unit, it will be, hopefully, it will be 1 picojoule per bit we can achieve if we have a very truly optimized RAN. 5G has a little bit off the mark, about 2 times, because the technology or the silicon technology, semiconductor technology is not able to catch up. Then, in this architecture, we have a decision to make because the energy is limited, has a ceiling. The computing, we can stack the GPU card to compute. So that means, do we spend more energy on the general computing for the connectivity, which is already optimized, or do we spend energy to do the intelligent computing to gain more performance and capability? So I think the ARAN part can do that, leave the optimization of the connectivity as it is, use the rest of energy and computing for the room to add more AI computing. Then ORAN doing the other way. That means try to use the general computing to do the already optimized connectivity. Then there will be not much of a room for the AI computing. The other part is the core network. So the foundation for core network is better to move or migrate to AI native because it's already in the cloud formation. So in this case, we need a couple of agents to construct the core network. First of all, you need a so-called net agent. When you understand what is the application, you can assemble the network component you need, and then you use planning, connection, execution, operation tool to assemble the network you want. When the application is done, these are all done. This is because the software development work is extremely simplified by the AI model. That is, use software to generate another software without human being intervene, or use a network to generate another network become running the AI model. So in that case, the net agent will construct the network, compose the network, and to run the network. And then the last piece is the device. Perhaps in a very short time, the device we know as Android or as iOS or as a Harmony may be over. It will take over by AI agent because the capability as the natural language to anything, it will be feasible. That is, we already see that Apple has aligned with the Open AI to deliver the ChatGPT service directly to the phone in the near future. So there will be a revolution of the AI. Yesterday, I didn't get a chance to comment on Peter's question of what is the phone revolution for the new phone. I think hands-free will be a symbol that we have a new phone. That means we don't need hands to hold a phone. That will be the new one. So to go back, the 6G is basically from large language model to AI agent. That is this year, AGI in 3 years. And then we take over as a connected AGI, and that is 6G and the AI will be meet together. Thank you.
Thank you. Thank you very much. Thank you.
Okay, so once again, the floor is open for questions. I don't see almost anything. Anyone? Okay, there's a microphone, please.
One quick question related to the resources. Do you see at the same time we'll connect the unconnected as well as we'll have AI in our pocket? So they follow different models, right? One is humanitarian, one is money-based, business-driven model.
Yeah, so there will be many models, but the capable one I'm talking here is the transformer-based model. This is the new AI I'm talking. So the CNN and all the other are not in this scope. And then the key part is the foundation model, that the model eventually will capture the human level of intelligence. That is the model, is probably the most interesting one, that in the end we have a long process of engineering, how to harness that model, become implementable. And as I said, if we only depend on the Moore's law, that model will be not in the pocket device. So therefore, we need a very good network to deliver this service.
Any other question?
Yes. Sir.
No? Okay, yes.
Yes.
One up there.
Hello. Okay, so it's here
Yeah, it's
to
okay.
the left.
Sorry, it's fine. Thanks.
Okay, hello. This is James Gross from Stockholm, from KTH. First of all, thanks for this very inspiring talk. I would like to ask you the question, you're certainly aware of these works on variational autoencoders for the physical layer. There's also work on so-called protocol language machines that try to substitute the network stacks. Now, you've been talking a lot about transformers and stuff on the application layer, but I think you have not really been addressing the question, will there be a standard for 7G? Is there a need for standardization in the future? And I think this is a very important question for the industry and here for the community. So maybe you could share your views on this.
Yeah, so the standards part so far is this so-called level A communication that, basically you need some physical parameter to interoperable. That's all we do today. I'm not sure, maybe 10 years later, those are the, become easy. I don't know. The one thing I didn't point out, this token is actually, I don't know the way to standardize that yet. It is model dependent. So then when we have a token communication, probably we need to have some model, at least at the LoRa level, the low rank adaptation in order to understand each other. Otherwise, it is very generalized. You don't need much of standardization on this level.
Okay.
Level B, level C, I feel comfortable. There may be not necessary standardization.
Okay, thank you.
Thank you. Then there was one up there. Yes, on the back.
Thank you. It's Izzat Darwaze from University College London. It's a general question really about, in the transformer model, the network demands are very high, and beyond the engineers, there is a huge worry about the energy consumption of 6G. And indeed, with all this incredibly sophisticated AI, the energy consumption is going to increase, I would say, exponentially. Can you comment on this, please?
Yeah, in terms of energy hungry, I think for us, the source is very clear. It is the AI portion of computing that is unbounded or uncontrollable at the moment. But for the connectivity, I already mentioned that optimization is needed. And some of the silicon process need more advanced to do. I don't know, but the AI for science will improve quite a bit of those things as well. You will never say they may find some semiconductor process or component to have a 90% of a PA efficiency. That's possible as well. So that we don't know, but the clear source for this is the digital computing for the transformer, as we say today. It's very explosive energy demand for that.
Okay, Wen, thank you very much. Wen will be around during the coffee break. I'm sure he will be available to entertain the rest of your questions. Thank you very much for such a wonderful talk. Again, don't drink it now. Wait for the... Just some housekeeping before you leave the room. You have two things to do today. One, until 4 p.m., you need to vote for the best booth. Use the app, the conference app, and vote for the best booth. We'll be announcing the results at the conference banquet tonight. The other one is there is an inquiry. You can do a survey, whatever you want to call it, at the app or at the website, where you can put all the complaints you have about this conference, about the weather, the food, everything else. Just put your complaints there. We'll try to do much worse next year. Enjoy coffee. Thank you very much for attending this session.